all. I hope you all are fine and safe. Okay, so today I'm having a great book with me in my tablet, and I hope you can see that this is the Irresistible Integrals, and we are going to just have a look like how this book is and what's inside this book. And I personally find this book as um, a deep understanding about integrals. Okay, okay, guys, and before everything else, we have an integral on the hard page itself that shows the integral from 0 to infinity of e to the negative x ln of x dx is negative times the Euler Mascheroni constant. I hope you are familiar with this. This is Euler Mascheroni. I think my spelling is kind of wrong, but yeah, adjust it right. Euler Mascheroni constant. This is just yeah. So I think these kind of integrals are being explained in this book, and this book is written by George Boros and Victor H. Moll. Okay, and here another integral is being shown over here. That is the integral from 0 to 1 of ln of gamma of x dx. That is ln of it's ln of square root of 2 pi. So yeah, it's gonna be interesting, and we are going to just have this. And before everything else, this is going to be my first video, and this is maybe I'm gonna just record all the videos in parts, and this is going to be the first part. Okay, so the first chapter is factorials and binomial coefficients. Okay, so first of all, let me tell you what factorial is right over here. So factorial, its notation is this: the exclamatory mark, I think. Yeah, so this is what does this means is n factorial. Well, n for our general knowledge, n should be a natural number, but when we will be studying about the Euler reflection formula, we can have the formula for like the factorial of half. Okay, we'll look at it. Okay, if this well, I'll tell you about this. Okay, but for now, we are going to just have n as natural number. So n factorial is just the product of n times n minus 1 times n minus 2 times, and this goes up to 3 times 2 times 1. Well, if you just plug n equals 5, okay, so we are going to have 5 factorial as n 5 times n minus 1, which is 5 minus 1, 4 times n minus 2, which is 5 minus 2, that is 3 times 2 times 1, and this is going to have 120. So yeah, and for your preference, let me tell you that factorials are not small numbers. Okay, and when you just have a look at 6 factorial, this is going to be 720. Okay, and for a reference that how big a factorial can be, well, just look at this factorial 52 factorial. What it might be like, what do you think? That maybe it's gonna be billions or trillions or more than that maybe, but you can't go up to 10 to the power 10 or 10 to the power 20, right? But the value of this is around 8 point something into 10 raised to the power 67, I think. So you can imagine that how this big number is. And for a reference, let's just introduce some astrophysics concept over here, that according to our Google data, we have the number of atoms, and I hope you guys are familiar with what is atom. Okay, the number of atoms present on earth is around 1.3 into 10 raised to the power 50 atoms only. So you can imagine that the atoms, like the pen I'm writing with has more than billion of atoms. So like the phone you are watching, the tablet or the laptop you're watching this video on, that is made up of billions of or maybe trillions of atoms. So you can imagine that this number is very 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 much big, even though we are having only 1.3 times 10 raised to the 50 atoms on whole earth. And again for a data the number of atoms. And I hope if you are like interested in astronomy, so you must have a got a question that Aman, just tell me how, let's just take it out, how many atoms would be in the entire universe, like in the observable universe. So number of atoms in observable universe is like is according to a Google data, it's around 10 to the 78 to 10 to the 82 atoms. So how you can imagine that? Well, I've talked about these two things, like the number of atoms I've talked about in a video, and if you want I would provide a link of that video. Okay, so I think we don't need to study more about factorials. Well, more specifically if I'm talking about, I'll be teaching. Well, I'm in class 12th, so like in education system like India's. So I'm in class 12th. So I'm just teaching this book specifically for integrals only. Okay, and well, it's not good for me, but I don't have a lot of knowledge about binomial coefficients. Well, I would study about this, but I'm not gonna teach you that. Okay, because I don't know. Well, it's truth. I'm not gonna lie over here, right? The method of partial fractions. Okay, so in these two things we are talking about functions, and you can see that elementary examples, Wallis formula. Well, I think we should check it out, right? Because Wallis formula is I think representing pi over 2 or something else. Let me just check it out. I think I have a phone and I have taken a picture of Wallis formula, and I'm just gonna tell you what's that. Okay, well, I love that because uh, that is a great representation of pi. Yeah, got it. So Wallis formula is like, according to my phone, I think I should just adjust it. 167. Wait a second, guys. Yeah, that's good. So yeah, pi over 2 is the product of 2 over 1 times 2 over 3 times 4 over 3 times 4 over 5 times 6 over 5, and so on. Well, it's not a perfect product, but yeah, well, if you want I would just propose a video to explain this, how is it possible. But yeah, it is representing the Wallis formula. Well, let's just check it out, right? It is on page number um, yeah, I think it's 32. So yeah, let's just move it on. 32. Well, it would be page number 32. So we are just heading to 21, 22 or something else. Let me just move on. Method of partial fractions, and 26. Wait a second, guys, let me just get over there. Yeah, here it is 32, and here we are having 32. Okay, so where is Wallis formula? Okay, so here it is. Let's just read it out. Okay, in this section we establish a formula of Wallis 1656, that is one of the first exact evaluation of a definite integral. This example will reappear throughout the book. Okay, so here we are not talking about that pi over 2 formula that I just told you right before on the context, but yeah, it's talking about integral. Well, yeah, that is also important. You need to just learn that. Okay, just check that out, the formula for pi over 2, right? And the first group uses the method to introduction of a parameter in order to evaluate an integral. One considers a more general problem obtained by changing numerical values by a parameter. In this proof we replace. Okay, so we have this integral, and it's kind of similar to the like when m is equal to 1, I hope you can understand that it's just tangent inverse of x evaluating from 0 to infinity, and it's just pi over 4. So yeah, it's a parameterization, like we're just parameterizing it, and let's say that it's I over I of m, okay, for our preference. And again introduce the parameter over here as b, and b could be anything. The extra parameter gives more flexibility. For instance, we can differentiate with respect to b. Okay, I got it. Parameterizing and then differentiating. So it's like talking about the Feynman technique. Okay, Feynman technique, that is, let's just parameterize an integral as I of alpha as something like dx, and there is a constant of alpha, and then just differentiate it with respect to alpha. So I prime of alpha is just the partial derivative of alpha with respect to alpha of this function and dx. So yeah, I hope you guys are familiar with that. Okay, so let's just yeah, so just differentiating. Okay, so what's this? I think it's a notation of some sort of. Okay, let me just get it. Okay, if m belongs to natural number, I think let's just do it. I think let me just think of it. We can differentiate with, okay, okay, so here we have just this is the final result. When you just evaluate this integrals, we are going to have this result. And here we have just assumed that our integral is like looking like this. As I told you that there are two variables b and m, so yeah, he just represented, like the author is represented like this: I of sub of m, I of b sub m. Okay, so yeah, not bad. So we are just going to differentiate with respect to b, right? And b must be greater than 0, and z of this sub 2 comma m is equal to I sub I of m, I of 1 sub m. Okay, so yeah, it's just you can see that this quantity is representing this integral. Okay, so when you just plug like 1, like on the place of b in this integral, when you just plug 1, so you're going to have this thing, that is this. Yeah, I hope you understand that. So yeah, he's just differentiating, and after differentiating this integral, he is going to have an integral, and we have a constant right before that integral, right, as this thing. So the initial value I of b sub naught equals pi over 2 root b. Okay, let me just check it out. M as 0. Okay, so when you just plug m as 0, so this integral is going to be an integral from 0 to infinity of dx over x squared plus b, and this would be 0, so it's 1, so it's nothing like disturbing us. So b is the square root of b and whole squared, and I hope you know that this is the tangent inverse of, well, 1 over root b, tangent inverse of x over root b, right, from 0 to infinity. So this is going to, I think there isn't any constant before. Yeah, there is a constant, that is 1 over the square root of 2, right? So 1 over square root of b, and tangent inverse of infinity over square root of b, just infinity, and minus tan inverse of 0 is a 0. So yeah, it's just pi over 2, so pi over root 2b. So I hope you understand that how we can easily calculate that integral, right? Well, let me not erase it, okay? So yeah, when you just calculate this thing, you're just gonna have pi over 2 root b. You can calculate this is very easy. Is a particular case of theorem 2.21. Okay, 2.2.1. now use 2.3. Okay, so yeah, it look guys, he is just calculating some values of m. After just plugging as m0, like we have m as 0, m as 1, m as 2, and maybe he's gonna just generalize it. The data suggests I don't know what is this, but again guys, let me tell you, I'm just a 12th grader student. Don't expect me a lot of things to just explain you, okay? Okay, I think he, like right over here we are having some sort of, okay, what's this guys? I'm not getting it properly. Okay, okay, let's just back to contents. I'm not just getting a lot of things, but yeah, still I'm just trying to explain you some sort of things that, where is, I think it's yeah. So we are having Wallis formula, the solution of polynomial equations, the integration of biquadratic. Well, I'm not talking about these things, but a simple rational function, multiple pole. Yeah, a review of power series, Taylor series. Yeah, we are just going to talk about these things, okay? And then we just move on exponential and logarithm function. Yeah, and now I'm kind of experienced and I have some sort of knowledge about these two things, like the chapter 4 and the chapter 5. So we are just going to heading towards those things. Chapter 4, yeah, a review of power series, and let's just check it out. I'm not sure, but yeah, okay. The class of polynomial function p of x is this thing. Yeah, we are just getting, but we are just continuing to study these things from class 9th, I think, and is the most elementary class considered in calculus. The goal of this chapter is to give a brief overview of power series. Okay, I'm having this, and these are representation of a function similar to, I don't know what this says, but in which the degree n is allowed to become infinite. Okay, so I hope guys you need to just read this out. This is just increasing the interest of us to study these things, like when you just have this thing like infinite. Oh man, I love infinite, okay? And you should also just love it, because yeah, it's a lovely thing. So what we are having is fx as this series from k equals 0 to infinity of ck x minus a. Okay, c sub k belongs to r. Okay, a power series centered at x equals a is a sum of the form. Okay, we'll understand it. I'm not having a lot of things. Most of the functions considered in this book have power series representations. Yeah, obviously, like I have studied about some sort of power series, and let me just tell you some sort of them, some of them. Like we are having the basic e to the x as the infinite series of x to the n. Well, let me just represent k as n over n factorial. For sine of x, n equals 0 to infinity of negative 1 to the n x to the 2n plus 1 over 2n plus 1 factorial. Cosine of x, infinite series from n equals 0 to infinity of negative 1 to the n x to the 2n over 2n factorial. Well, please don't talk about the infinite series of tan of x because it consists of Bernoulli's constant, and we'll talk about this later. Okay, well, like we cannot understand this thing right now, but yeah, we'll talk about what is Bernoulli's constant or what is Bernoulli's constant. Okay, so yeah, these things are the most basic things. And you know what, like if you look closely, then let's expand this thing. So we are having e to the x as x over 0 factorial. Well, no, yeah, expand this thing. We are having x to the 0, which is 1, plus x to the 1 over 1 factorial. So x over 1 plus x squared over 2 factorial plus x to the third over 3 factorial plus x to the fourth over 4 factorial, and this goes on. And yeah, this thing is related to the derivative of e to the x to infinite. We'll talk about it. Okay, just keep remember this thing. So yeah, and that's why here this book says that most of functions considered in this book have a power series representation. This includes the advanced functions that appear from blind mathematica evaluations. For example, the hypergeometric function is defined by power series. Okay, you know what hypergeometric function is? If you don't know, let me just tell you right over here. So hypergeometric functions are like this. Sinh, well, it's our day-to-day language to say this, but yeah, this is hypergeometric sine function, and same as hypergeometric cosine function. And there are also infinite series of these two functions also. Well, we'll tell you. Okay, I'll tell you about this. You know what, like why these things should be introduced in our education? Why, like why do we have to study these things? To make our life easier. Okay, and we'll tell you again, just be patient. So, and given a value of x, let me just use the highlighter. Given the value of x, this sum becomes a real number such as not converge. A simple argument shows that the set of points x for which the series converges is an interval of the form a minus r a plus r, called inverter of. Well, we do not need to understand these things, but yeah. Okay, so when, like, if you have completed your class 11th, and if I'm talking about in India, then in class 11th there is a chapter of sequence and series in mathematics. Okay, sequence and series, and when you must have studied in that chapter an infinite GP, infinite geometric progression. Okay, so if well we just well we use, like, I used to study this, and there is a formula for an GP that is represented by this: a times ar times ar square times ar cube times dot 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 to infinity is just 1 over 1 minus r. Well, it's a over 1 minus r actually, and r is less than 1. So yeah, this is the formula for that thing, and that's what we are studying here. So this is just that thing, like this thing is represented in this way. So the you have to study this, you have to just keep remember, because this is very important. And yeah, this is like, wow, just have a look at this. The infinite series from k equals root infinity of x to the k is 1 over 1 minus x. Like, wow, this is crazy, right? Let's put x as um x as -1 to make our life easier. So when you just put x as -1, so this series from k equals 0 to infinity of -1 to the k is just 1 over 2. How crazy this is. Like, you can replace 1 over 2 as this thing. So yeah, this is really crazy, and I love to just study this. Every time I feel wow when I study this thing. And again, when you just look at this thing, this is also something, some sort of like that. When you just have this series from k equals 0 to infinity of -1 to the k x to the 2k, it's like, just look at this. You can just replace this thing by this thing. Wow. And hence you can, like, I'm just going to write something over here, be careful. You can replace any function or any quantity by its infinite sum. How cool is this? Like, just look at this. When you just, let me explain this thing, okay? When you just add -1 to the k as this thing, like, just let me expand this, okay, for our okay. So let's expand this. -1 to the 0, it's just 1, okay, 1. And -1 to the n is -1, +1, -1, +1, -1, +1, -1, and this goes to infinity. And this is just 1 over 2. Like, how cool this is. And I just want to explain you something about this thing. So I'm just going to write this thing over here, and I'm just going to erase all the stuffs. What we had, we had the infinite sum -1 to the k as 1 over 2. Okay, before everything, let me just change the color of this thing. So yeah, just expand this, okay? Let's expand this. So we are having -1 to the 0 plus -1 to the 1 plus -1 to the 2 plus -1 to the 3 plus -1 to the 4, and so on, so 2. It's 1 over 2, because according to our formula it's true. So what's -1 to the 0? It's just 1. -1 minus 1 plus 1 minus 1 plus 1 minus 1, and so on, is 1 over 2. And when you look closely, this is cancelling out, this is cancelling out, this thing cancelling out, and so on, so on, so on. But again, we are not getting 0 as our answer. And you know what contradicts over here? The contradiction just getting born is the infinity. This is what we don't know about, and that's why it's just playing with us. Because it's impossible that, like, okay, let's have another series. I'm just telling you that an infinite series, let's say this is going to z, okay, from k equals 0, and limit z does not tend to infinity. Well, for more precisely, it's a constant. Okay, z is a constant, not infinity. Okay, and negative 1 to the k, so it is 0, because you can, or let me just erase this, because some of you would tell you that it's not, it doesn't mean any two. So z is constant, z is not equal to infinity, like z is not tending to infinity. Let me just tell you that. Okay, it's is not tending to infinity. Yeah, that's what I'm talking about. So this is going to be 0, because it's just cancelling out. It's a telescoping series, and these things are going to be cancelling out each other. So this is eventually we're going to have 0 as a result. But the fact that here we are having this thing, when you just can when you just look at this thing, so let's replace this infinity with the z. And you know what z is? Limit z tends to infinity. And that's why this thing is true, because when you have to just plug z as infinity, right? But when z is a constant, you're just gonna have 0 as an answer. But because z is infinity, that's why you are having this thing as 1 over 2. Well, it's impossible to believe, but yeah, it's true. So well, we'll talk about this later, because it's really interesting, and I'm just feeling very good after talking about this thing. But yeah, you need to just check it out, guys. It's very interesting. And let's move on further. Where we are, yeah, here. So yeah, it's also when you can plug anything on x, and this is what we need to just check every possible x's. Like when you just plug x as 0, so this is, no, it's x is x cannot be 0 obviously. But well, let's plug x as 1. Okay, again we are having 1 over 2 here, and x as 1. So yeah, the same result we are having. But let's plug x as 2 in this thing, x as 2. Okay, then what we're having, that this is 2 to the 2 to the 2 times k, so it's gonna be 4 to the k maybe, right? So it's 4 to the k. So this series becomes the infinite series of negative 1 to the k times 4 to the k. And when you just solve this infinite series, you're going to have as the result as 1 over 2. As we have, well, it's pretty hard to believe, and oh my god, this is gonna blow my mind, dude. But yeah, let's just take this also out. Let me just copy this thing. The way I copy some sort of informations to some places, and this should be deleted right away, and we're just gonna paste it right over here. So yeah, just look at this. Why I just took this here? Because when you just plug x as 1, yeah, sorry, no, x not 1 but x as 2, yeah, so it's gonna be 1 over 5. Okay, yeah, that was true. And let's move on further in our book. Okay, just there is an information written over here. Observe that the function f of x as 1 over 1 minus x is a well defined on R, with the single exception x equals 1, right? Because its power series representation centered as x equals 0 converges only on yeah, this thing. The incorrect use of f outside its radius of convergence is at the center of it of false identities. Like, okay, what's this? Let me just conclude this thing. So when you just plug x as 2, when you just plug x as 2, okay, yeah, so it's just talking about the boundaries of x. because this thing, like, just look, the presence of discontinuity at x equals 1 is reflected on in the interval of convergence of this series representation of x. For x, this phenomenon is sometimes harder to visualize. The function in the left hand side of 4.1.4 is well defined for x belongs to R 4.1.4. okay, but what about the convergence, but the series convergence only of for, okay. So yeah, there are some boundaries, obviously, because we cannot compute everything as we wanted, because yeah, it's just look at this, dude. And the same thing, like, I hope you know that the Ramanujan's infinite series of natural numbers, this is 1 plus 2 plus 3 plus 4 plus dot 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 to infinity is just negative 1 over 12. And again, I have a topic to explain this thing in a video, in a specific video, and I will do that. Just wait for that moment, guys. And here we are having, well, let's just I hope that if I'm getting wrong somewhere, then help me out, guys, because again, I'm just telling you that I'm just a 12th grade student. I have to know a lot of things. I'm not a graduated guy, I'm not a professor, okay. So here we are having dialogue function. Well, what is dialogue function? The dialogue logarithm function, I think it's represented like this. So the infinite series of this function is as explained over there, that is x to the k over k squared. Keep remember, guys. Okay. What? Okay, let's just study this out. Let's just read it out. It is surprising fact that the functions defined by power series with coefficients given by a simple formulas are sometimes not elementary. For instance, the dialogue function defined by defined by this thing was considered by Euler, and after a period of silence, it has reappeared in many aspects of modern mathematics. The reader will find in Levin in 1981 a fascinating collection of a result, including the evaluation. Okay, so Levin evaluated an integral like this, and like this function is really popular, ln of 1 minus x over x, and this thing represented by ln squared of square root of 5 minus 1 over 2. And you know what, like, maybe I'm correct, but this is the phi function. No, it's psi function, I think, because it's the solution of x squared plus x, no, x squared minus x minus 1, I think. Yeah, it's okay. Oh, guys, okay, let's just have this. That's what I'm talking about. That's what I was talking about, the infinite series of tangent of x, including the Bernoulli's number, as I told you, guys. Well, I have studied about this thing. So the tangent of x equals the infinite series of k equals 1 to infinity of 2 to the 2 times k times 2 to the 2 times k minus 1 over 2k factorial of the what do you call, the mod of Bernoulli's number sub 2k times x to the 2k minus 1, where b sub 2k are the Bernoulli numbers. These numbers will be considered in chapter 5. Okay, we'll talk about this. And Taylor series for the tangent is established in 6.9.5. yeah, Taylor series established. Okay, we will have the proof of this thing in on this thing. Okay, in this text we will note. Okay. Let's just move on further. Yeah, guys, this is very important. That just relates and not infinite, but yeah, an integral with a infinite series. Okay, heading towards to have something better, but I'm not having. Okay, so now we are talking about Taylor series. The behavior of a function near a point x equals a can be determined by expanding f in powers of x minus a. For example, the binomial theorem yields x to the n. Um, yeah, this is interesting. And we are just going to talk about. So yeah, guys. Yeah. This is talking about a function near a point x equals a can be determined by expanding f in powers of x minus a. So yeah, this is another well, it's obvious. I don't know what this is, but yeah, it's talking about binomial theorem, and that's what I never. But I studied, but no, never studied seriously. That's why I'm sorry, guys. I cannot explain you these things. But yeah, I need to study for understanding the Taylor series, the basics of Taylor series, right? The Taylor series of a function f of x centered at x equals a is the sum. Okay, so yeah, this represents the jth derivative. Oh, yeah, guys. Do you remember that in the expansion of e to the x, I told you that it was x 1 plus x squared over 2 factorial plus x cube over 3 factorial, and this is what we are talking about. This thing, like, wow, guys, this is f of x, right? You know what, that this represent the derivative of that function at jth time. Like, yeah, I'll explain you. And f of a, we are talking about like, if f of x is e to the x, then find the derivative of at jth time at x equals a. So e to the a. Yeah, I think this book will just explain why e to the x is represented at the infinite series of x to the n over n factorial. Well, guys, while I was teaching you guys, and my mom brought a glass of milk, and I'm just having it because in my area it's kind of cold, and my hand is kind of being what do you call it, cold, and I'm not properly teaching you guys, but yeah, I'll do it because I'm having fun. Use the Taylor series f of x equals x to the n plus 1. Okay, so now this book is going to just have the Taylor series of x to the n plus 1. I don't know what this is representing to us, but well, I don't know, sir. You asked me the direct proof, but I don't know about that. 1 plus x to the n equals this thing. Well, binomial, I have to study it because I'm not having proper knowledges without binomial thing. So I have to study binomial theorem, and I think I'm just gonna have to study this after this video. But I'll explain you all of these things, guys, when I will have a lot of knowledge about binomial theorem. Okay. Prove Cauchy's formula. What is Cauchy's formula? Well, I know about this thing, guys. Like, this man, he had contributed a lot in what do you call it? There is a branch of mathematics. I'm not quite remembering, but we talk about the complex numbers, the integrals of complex. Well, let me just check it out because I have to. I think it's analytic. Complex analysis. Yeah, guys, I was talking about complex analysis. So this man contributed a lot to complex analysis along with Riemann. And I hope you what Riemann, what was Riemann. There is a Riemann hypothesis, and well, if you solve the Riemann hypothesis, you can win $1 million. uh, well, we are not going to talk about that, but yeah, there is infinite sum of Riemann that is like this. Riemann of z, like the z of z, is the infinite series 1 over k to the z. No, I'm sorry, guys. I think it's z to the k, because 1 over 2 plus 1 over 2 squared, 1 over n squared. So no, sorry again, that was k to the z, and this is what Riemann of z is called. But we're not going to talk about this. Maybe this book will just have some knowledge about, well, maybe this book is going to make understand about those things. And again, I'm just not having a lot of things right here. Taylor series for rational functions. What is this? Okay, yeah, I know that. Okay. I think I should just move because I'm not understanding a lot of things. I have to study the binomial coefficients. And yeah, this book is for the graduating guys, not for 12th guys. Okay, now we are just heading towards this thing, the exponential and logarithmic functions. Okay, the rule of integration. Okay, wow, that's great. The integral, well, I'm just going to explain you. The integral from 1 to x of t to the n dt equals x to the n plus 1 minus 1 over n plus 1. Well, it's just a normal method of integration. So he is just integrating 1 to x of t to the n dt. It's just t to the n plus 1 over n plus 1 from 1 to x. So x is going to be replaced by, like, t is going to be replaced by x. So x to the n plus 1, and 1 over n plus 1 minus 1. T is going to replace by 1. So 1 over n plus 1, that is x to the n plus 1 minus 1 over n plus 1. Yeah. So yeah. So that's what it is writing. What it is written over there, right? And I hope you know this thing also. The integral of 1 to x, or the integral of dx over x is ln x plus c. It's a basic thing. And let's just read these things out. We also introduce one of the basic constants of an Euler number, that is E. Yeah. So yeah, it's just talking about the most basic things in integrals, obviously. Like, at first he just explain the integral, and again, and that's why this book is the Irresistible Integrals. Wow, you'll have to listen. And what, well, the integral is just the antiderivative, right? Antiderivative. So the derivative of that function would be, like, if we are talking about the antiderivative of ln x is just x. So the derivative 1 over x actually. So the derivative of, no, sorry, the antiderivative of 1 over x is ln x, right? Like the integral is the antiderivative, or just leave it. Listen, um, derivative is opposite process of, oh wow, my writing is quite good, opposite process of integral. So when we are having like the integral of 1 over x dx is ln of x, then the derivative of ln of x is 1 over x. This thing should be remembered by you guys. That's what here the author has represented. And these are some sort of basic formulas for the logarithm. You need to just I'm not going to explain you everything right in this video, but yeah, you can just check it out. It's basic things. Let's just move. Yeah, here it comes, the infinite series of ln of 1 plus x. Wow. So ln of 1 plus x is represented by the series of negative 1 to the n minus 1 over n x to the n. And when you plug x as 0, no, well, this would be 0 and this is also going to be 0, but well, let's plug x as 1. So this is going to like negative 1 to the n minus 1 over n, and the infinite series of this thing is just ln of 2. That's good thing. You can just check those things out, okay? And again, when you just look at this thing, what it is, it is the integral of 1 over t plus, sorry, x plus 1 dt, or more precisely 0 to x of t plus 1. That's what here the author has represented. So now you can just see that this integral of 0 to x of dt 1 plus t over 1 plus t is the infinite series from, well, let's say n equals 1 to infinity of negative 1 to the n minus 1 of x to the n over n. And why n is not beginning with 0? Because of this thing, because there is an n in denominator, that's why. And you can just, like I told you na, here where when you just plug x as 1, so you're going to be ln 2 as this thing. And this is justified by Abel's limit theorem. Assume that we have fx as this thing if fx lies between negative r and r. Okay, well, what r is the common difference, no, common ratio actually, sorry, not common difference, because common difference was in arithmetic progression, but in geometric progression we are having a common ratio. Let's move further. And there is again an infinite series of ln of 1 minus x. And look, you can prove something better for yourself from this formula. And how so? Let me tell you guys, don't worry. Let's plug x as 1. I think I should slightly bigger the size of pen for your convenience. So x as 1, okay? So this thing would be ln of 0. And from now, if you are having something ln of 0 type of concept, then you're going to use this thing. How so? Then just plug x as 1 in this thing. So the series, negative of the series from n equals 1 to infinity of 1 to the n, that is 1 over n. And this is negative of zeta of 1. I hope you remember that. And negative of zeta of 1 is indeterminate, like it's not well, it's infinite actually, indefinite actually. So it's not a finite value, it is divergent. In simple ways, in simple language, it is divergent, and hence ln of 0 is also divergent, or it could be infinity, or because of there is a negative sign, maybe it could be negative infinity, and that's why is taken as negative infinity, ln of 0. And hence if ln of 0 is negative infinity, that's why I'm just taking e both sides, then we are having 0 equals e to the negative infinity. And this thing is quite useful in every manner, like I have used a lot of times this thing. So this, you need to remember this because it's really helpful for us. What's e to the negative infinity, guys? It's 0. We can prove this by using this thing, right? Yeah. Okay. As far as my knowledge, this represent harmonic function, and I don't have a lot of knowledge about this. I'm really sorry. Here you can check it out. And this thing is what? H of n. Okay. Guys, we are having ln square of 1 minus x as this infinite like representation, right? And when you remember that ln of 1 minus x, it was represented as what was that? That was x to the n over n. And when you just multiply these two things, then you are going to have ln cubed of 1 minus x and 2, like negative 2 times this infinite series. Like here that is being represented. Okay, I'm not going to explain you anymore because in terms of harmonic numbers, okay, let's just move further. Okay, look at this. Let's have a look at this. Limit x tends to infinity of ln of x is infinity, like ln of infinity is infinity. So infinity is equal to the e to the infinity, right? But e to the negative infinity is 0. Keep remember that. So wherever, if you're looking at, like, look, yeah, you can understand that when you have to use infinity, and when you have to use 0. Let's move further below. Well, this looks cool. What was harmonic number, it was 1 plus 1 over 2 plus 1 over 3 plus dot 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 plus 1 over n. You need to remember this. Right? And this looks quite good, I think. And I think that this appears in Clamkin. I think I should check the proof of this thing, like how this thing is. Wait a second, guys. I'm just looking at the proof of this thing. No, it's not easy to evaluate. But please, guys, for whatever question you want to know the proof, like for whatever you want to know the proof, like if you want to know the proof of this thing, then just comment me with the timestamp, and I will try to just come up with the proof of this thing. Okay. Okay, let's move further below down, and I'm having something here. The series from k equals 1 to n minus 1 of ln of 1 plus 1 over k, like this thing. Ln of 1 plus 1 over k is ln of n. Okay, let's say that let's play with some sort of mathematics. Okay, let's plug n as 0. So we are having this series from k equals 1 to negative 1 of ln of 1 plus 1 over k equals ln of 0, that is negative infinity. Yeah, this is impossible, and that's why it comes out to be negative infinity, because you are adding from 1 to negative 1. What is this? Like, how is it possible? We have to just battle with mathematics, and that's what I'm studying this thing, because I have to battle with mathematics. I just want to prove something wrong. That's why. And let's just have a look at this. As x tends to infinity, what? Like ln x. Okay, look, limit as x tends to infinity of ln of x over x to the a as 0. How, dude? Like, when you just plug x as infinity, let's use L'Hopital rule to make our life easier. And okay, look, I have to copy this thing, and to solve this thing, to prove this, let's use it. And I have to find a blank page. Look, don't forget that, where yeah, page number 79. Okay, just guys, keep remember that, page number 79. Oh, just get me a blank page. I just want to, well, please don't disturb me. Well, I'm not having a blank page at all. Let me just get back to that page. We were on 79, right? Let's just go upward. Maybe we can find Yeah, so we are having this thing, and I'm just going to erase all these stuffs. Yep, paste. Okay, using L'Hopital rule, Hospital rule, like limit x tends to infinity of d over dx of ln of x over d over dx of x to the a. Well, it's gonna be 1 over x over a times x to the a minus 1. So 1 over a is a constant, and well, let's just don't forget the limit. As limit x tends to infinity, as limit x tends to infinity, 1 over a is a constant, and we're having x 1 over x and times x to the a minus 1, which is x to the a. Okay, so this is 1 over a times 1 over infinity, that is 0, and hence it is 0, right? So yeah, this is right. Obviously I'm not gonna prove this thing wrong at all. We were on 79, right? Yeah, here we are. Okay, let me just have some water. You know what, guys, it's my personal thing, but I want to share it with you. I just hate chemistry because it doesn't have any sort of logic, and again, I don't like it. That maybe that's why I don't like. I don't want to study it. Guys, please keep remember there should be a plus c. Keep remember that the integral of ln of x equals x ln x minus x. Okay, and again, establish the formula. You need to remember this thing also. It's quite easy to evaluate. Like if you want me to evaluate this thing, then just using di method, ln of x plus minus is 1 over x and 1 x, this thing and this thing. So it's gonna be ln x times ln of x and minus, when you in an integral, 1 over x times x dx. So x got cancelled out with the x ln x minus the integral of dx, which is just x. So hence we have evaluated this as x ln x minus x plus c. This is easy to evaluate. Okay, just use the by parts. Wow, just being happy to look at this thing. The integral of ln to the n x, like the integral of ln x to the n is negative 1 to the n times x of this series from k equals 0 to n of n factorial over k factorial of negative ln x to the k. And I would like to see the proof of this thing. And guys, maybe I'm just gonna put this thing in the next video. I'll bring a proof of this thing. Okay, let me just have a picture so that I won't forget. Yeah guys, I just got a picture of this thing and this looks quite good, and I would bring a proof. Okay, let's just move further, and I think I should just get back to contents because I'm not having a lot of things right here, and I would be going to integrals as I'm a lover of that thing. Stirling's formula, some definite integrals, Bernoulli number. Quartic integral. Okay, I think I should move to chapter 7 because the normal integral, Euler's constant, existence of Euler's constant, the second proof of existence of Euler's integral form of Euler constant, the rate of convergence of Euler's constant. Yeah, I think as Eulerian integrals. Yeah, guys, I think I should move to chapter 7, and then maybe in the next video I'll bring up with next to next, or maybe after some videos, because I have a lot of things to prove after write this video, because a lot of things we didn't get well to understand. But yeah, I will try to just explain all the things what we didn't understand in this video, and I will try to just bring some sort of videos to explain all the stuffs. Well, this book is really wow. Here we are talking about like the Riemann zeta function. This is the representation of zeta of z is the series, infinite series, I think from 1 to infinity of 1 to the k to the z. Zeta of 2 is a Basel problem, it known as it. And you know what, the value of this thing is just pi squared over 6, right? And zeta of 3 is divergent, but it's called as Apéry's constant. And well, a lot of things we have to deal with. Sklom-Mills transformations, derivative or derivation of master formula. This book is really interesting. And well, the hardcover, the hardbook of this book is quite around maybe $100. But yeah, if I don't have money right now, but if I would buy this book right away, because this book is consisting a lot of things that would be helping me to better myself in chapter 7, page number 135, right? Let's just move it on. 135. Yeah, we're on the right track. Aquatic integral. What it is? I think, guys, I should just cut this book right now, but I think I should just get back to the proof of the what do you call the thing that, let me just write it down to make you remember what I'm talking about. It's the integral ln to the ln of x dx is negative 1 to the n times x times the infinite series. No, it's not infinite, but n from k equals 0 of n factorial over k factorial of negative ln to the ln x to the k. Okay, let me just look at the proof. Well, guys, look, wait, guys, wait, and not screenshots, but all the things. Okay, so do you want to, I'll use again the Google, I will not be lying, but I would try to explain you everything. The equation is correct, but I just want to have the proof, bro. Google. Okay. Oh. I think I should again to change my plan. I have to change my plan. I would bring this proof in the next video maybe. So guys, I think I don't want to quit right now this video. So let me just have another book if I have to to teach you. Wait a moment, guys. And so, guys, I think it's around more than 1.25 hours, and I think I should just cut off the video because it's quite a long video I have made. And I hope whatever we studied in this video is clear to all of you guys. And just wait for the next video. Thank you for watching this video, and have a good day, guys. Thank you so much.